So welcome to the video. Today we are going to take a look at how to do a paired t-test on version 31 of SPSS. So we're going to use this test when we have continuous data for our dependent variable and when we have an independent categorical variable comprised of two levels, and when that is a within participants or within subjects categorical variable. So for this example, we are going to imagine that we have given some participants a task to do and we're assessing how quickly they react to something. So we're measuring reaction times in milliseconds, and we are assessing whether their performance on this task is influenced by the application of transcranial magnetic stimulation to their heads, so otherwise known as TMS. So in this A column, we have their reaction times for before TMS, and in this B column, we have their reaction times for after TMS. So the paired t-test is going to tell us whether there's a significant difference in those reaction times between before and after transcranial magnetic stimulation. So let's take a look at how to put these data into SPSS. So the first thing we'll do is we'll go down to variable view, and then we'll give a name to one of the levels of the independent variable. So let's just call this before as a shorthand for before TMS, and we'll say that the other level was called after as a shorthand for after TMS. So once we've done that, we can go over to this measures column and we can say that we have scale data, which is another way of saying that we have continuous data. So let's go down to data view and we can see that we have before and after now at the top of these two columns. So I'll go back to my spreadsheet and I'm going to select the top left piece of data. I'll scroll down and then while holding shift, I'll select the bottom right piece of data. I'll then go to Command or Control C to copy those data. Then I'll go back to SPSS and I'll select the top left cell and I'll press Command or Control V to paste those data in. Sometimes that doesn't actually work, that pasting step, in which case you should just go to Edit and then down to Paste, and that usually does the trick. So one of the assumptions of this test is that the differences between the two time points are normally distributed. So to check this assumption, we actually have to create a new variable. So to do this, we can go up to Transform and then down to Compute Variable, and then we can transfer before over to this numeric expression box by using this arrow. Then we can enter a minus symbol, and then we can transfer after over here as well. And then we just need to give a name to this new variable that we're going to create. So I'm going to call it difference. Then I'll go to OK, and that will create the variable for us. And just to explain what this is, if it isn't clear, we have a value of 329 milliseconds here, and we have the value of 311 milliseconds here. So if we deduct this value from this value here, we have a value of 18. And now we can use this variable here in an analysis to determine whether these values are normally distributed. So to do this, we can go to Analyze, and then down to Descriptive Statistics, then across to Explore. Then we can transfer this difference variable to the dependent list box. Then we can go to Plots, and then we can untick stem and leaf. We'll tick histogram, and we'll tick normality plots of tests. Then we'll go to Continue, and then to OK. And then if we look at this test of normality table, we can see that we have two tests within it. So we actually have the Kolmogorov-Smirnov test on the left, and we have the Shapiro-Wilk test on the right. And typically when we have fewer than 50 rows, we're going to use this test on the right. And when we have more than 50 rows or participants in this case, we're going to use this test on the left. Since we have 30, we're going to focus on the Shapiro-Wilk test. And we're going to look at this SIG column, where we have a value of 0.317, and as this is above 0.05, the results suggest that the data are normally distributed. If we scroll down slightly, we find this histogram, and when you're looking at histograms to try to determine whether the data are normally distributed, you want to see that you have a symmetrical bell-shaped distribution. This histogram isn't particularly convincing. It somewhat corresponds to that bell-shaped symmetrical distribution, but not especially. However, I tend to prefer to use these normality tests because they provide you with a more objective answer as to whether or not your data are normally distributed, because you can see, is my value in the SIG column above or below 0.05? So let's say that the data are normally distributed based on this Shapiro-Wilk test. and we can continue with running the pair t-test. However, I will just point out that if you do find that your data are not normally distributed, you could consider doing a Wilcoxon test instead, which is the non-parametric equivalent of the pair t-test, and it doesn't make this assumption about normality. So to run the test, let's go up to Analyze and then down to Compare Means and Proportions, then across to Paired Samples t-test. Then we just transfer before and after over here using this arrow. And then we go to OK to run the analysis. And then we can look at this paired sample statistics table. And if we look at this before row, we can see that we have a value of about 316. So that's the number of milliseconds required on average for someone to react during this task. And in the after row, we have a value of 292. So we can see that we have a lower value after compared to before, suggesting that after the transcranial magnetic stimulation, the participants were a little bit faster during this task, so their reaction time was lower. And if we look at this paired samples test table and at the significance part of it, we can determine whether or not this difference we've seen is significant. So we actually have two columns here. We have a one-sided p-value and a two-sided p-value, and which of these you look at is determined by whether you had a one-sided directional hypothesis or a two-sided non-directional hypothesis. So in this case, a one-sided hypothesis would be something like it was hypothesized that reaction times would be significantly lower after TMS compared to before. And a two-sided hypothesis would be something like it was hypothesized that there would be a significant difference in reaction times between before and after. So with the one-sided hypothesis, you're predicting which is going to have the higher or lower value. And with the two-sided hypothesis, you're just saying that there will be a difference. So let's imagine that we had a one-sided hypothesis, and we're going to look at this value here, and we can see that it's less than 0.001. And as this is less than 0.05, it indicates that there was a significant difference in the reaction times before and after TMS. So that's essentially how we interpret these results. But let's now take a look at how we can report them. So I have an example here, and I've started off just by saying that a paired t-test was conducted to compare reaction times before and after TMS. Then I've said that a Shapiro-Wilk test indicated that the differences between the time points were normally distributed, and then I've reported these statistics here. So we have a W value of 0.96, and if we go back to the output and we scroll up to this test of normality table, we can see in this column here that we have a value of 0.960. So I've just rounded that to 2 decimal places in the results section. We have the degrees of freedom value of 30, and we have a sig value of 0.317. So here is the degrees of freedom value, and here is the P or sig value of 0.317. Next, I've said that reaction times were significantly higher before TMS compared to after, and I've inserted means and standard deviations for both of those time points. So here are the statistics for before. So I've said that the reaction time before, or the mean reaction time before, was 316.30, and that's coming from this paired sample statistics table, where we have this mean here in the before row of 316.30. We have a standard deviation of 30.63 if we round this to 2 decimal places, and that's what we have here. And then we have the means and standard deviations for after TMS, which are just those in the after row, so here and here. Next we have the results of the t-test itself. So we've said that t equals 8.65, and that's what we have here in the paired samples test table, and in the t column we've just rounded this value to 2 decimal places. We have a degrees of freedom value of 30, and we have a one-sided p-value of less than 0.001, and that's what we have here. So there's the p-value, and there's the degrees of freedom value. And finally we have this sentence that says the effect size was large, and we have a Cohen's d value of 1.58, and that value is coming from this paired samples effect sizes table, and from the Cohen's d row and the point estimate column, where we've rounded this value here to 2 decimal places. And we've described that as a large effect, and that's based on these criteria here. So typically values between 0 and 0.2 represent very small effects. Those between 0.2 and 0.5 represent small effects. Those between 0.5 and 0.8 represent medium effects, and those above 0.8 represent large effects. And the same thresholds apply if you have a negative value. For example, if you had a value between negative 0.5 and negative 0.8, that would be described as medium, just as a positive value between 0.5 and 0.8 would also be described as medium. So here we have a value above 0.8, so we've described this as large. So that's essentially how you report the results of the test. I hope that was helpful. If you have any questions, just let me know in the comments and I'll try to get back to you. Thank you very much for watching, and I'll see you next time.